The next exponential function we're going to look at is called the natural base e. E is named after Leonard Euler, who actually computed this number to 23 digits. And what it is it's this number that shows up in nature, in money, in finances, in different places. And what it is it's derived from this limit right here, the limit as x approaches infinity of 1 plus 1 over x to the x power. Now what you'll notice is as x continues to get bigger, we get closer and closer to this number. It's like when we use an approximation, a rational approximation for pi, 3.14159, right? Well, for e, named after Euler's number, it's going to be 2.71828, right? And so on and so forth. And our calculators use 9 digits, and that's basically what we're going to go with, okay? Now, this has huge implications later on, and we're going to talk about those later. But for right now, let's look at some graphs and see some translations between them. Okay, so let's look at e to the x. So we're going to start by going to Desmos, and we're going to graph e. Now, you're probably wondering how you get e. Okay, well, if you go to Desmos, down in the bottom left corner, there's the ABC button. And so if you click on that, you just put e, and you'll actually notice Euler's number shows up, 2.71828, right? So that's how we get e. Now, let's just graph it, go back to numbers, to the power of x. Okay, so here's our graph. It crosses at 0, 1 still, because anything to the power of 0 is 1, right? And when we put in 1, we get this right there, like 2.1828, right? Right about there on our graph, okay? So we're going to keep that in blue. Now, the first one, example A, asks us to look at e, okay? So we go to e to the power of 4x and see what happens. Now, what do we notice? It still crosses at 0, 1, right? It still crosses there, but we notice that our graph jumps up real fast, real quick, right? So what ends up happening is our graph is stretched by a component of, or a factor of 4, right? So we're actually going to say that what this does is it stretches graph f of x by factor 4, right? It stretches it by a factor of 4, okay? Now, let's look at letter B. Now, in letter B, we're looking at b of x, and it's e to the negative x plus 3, excuse me. So we go to our graph, right, and we're going to go e to the power of negative x, and then negative x, and then we're going to do plus 3, right? So what happens? Well, okay, so we're looking at the purple graph. We see that when we have a negative exponent, it flips over the x-axis. We knew that. And this is going to change it. It's going to translate it vertically up by a factor of 3 because we have plus 3, right? So we go here, and we know flips over the y-axis and translated up 3. Okay? Next one, we're going to look at c of x. Okay? Now, c of x is 1/2 e to the x. So now we're not doing anything to x. We're just multiplying it by some factor. Okay, so we get rid of this. All right, we're going to do 1/2, and it's going to be e power of x. All right, and so you'll notice my whole graph looks very similar. The only difference is that I have it now squished, compressed by a factor of 1/2, or I guess it's compressed by a factor of 2. I guess we can call it that. All right, so this one right here is going to be compressed, and we can even be more specific. It's compressed vertically by factor of 2. Okay, so we've taken it and we've compressed it down. So here's a couple examples that I would like you to look at and try and graph them and see how their translations change.